So we were in the last class, we saw some applications of linear periodic time variant systems. Uh, um, all of you were there in the last class. It was not recorded. Anybody who was not there? I think all of you are there. Okay, fine. So if that's the case, so what I would like to do is take that specific example that I talked about in the previous class, and then use it as a vehicle to understand LPTV systems. Okay, so what I mean by that is we'll try to understand how, let's say I have a switched RC network. Where S of t is periodic with some duty cycle, so on. Say this is Ts, and let's say this is T on. And SB of t is the inverse of this. So right. And your input is Vi, and I would like to find out what is the voltage across the capacitor. With regards to, I want to find out the transfer function from Vi to the voltage across the capacitor. Okay, so when I say transfer function, firstly, this is not an LTI system. So it's not necessary that I should be able to talk about a transfer function, right? So, but from whatever we know, we should be able to, we know that it's linear. We know this is periodic. We know this is time varying. So which means that if I apply an input e to the power j omega naught t, the voltage here V naught should be some h of j omega naught t times e to the power j omega naught t. Right? This we understand, right? You recall? So I want to find out what this is. If it were a LTI system, then h j omega naught t would have been independent of t, right? But it is not an LTI system, so it makes sense to assume that it will be dependent on t. Okay. In a very rudimentary sense, it should be apparent, because if the switch S of t is on, that is, I'm talking about this region, then clearly the input is connected to the capacitor through a resistor R. You are expected to have some type of waveform. When the S of t is off, right, the voltage across the capacitor cannot change. It has to be a held value of the waveform that the capacitor saw at the falling edge of S of t. Right? Does that make sense? So basically what I'm saying is that you are going to have you are expected to have a different envelope when S of t is high, and you are expected to have a different envelope when S of t is low. Right? So, and this whatever in a steady state, whatever is happening within any period Ts should repeat for all periods, all subsequent periods, right? So which means that it is sufficient for us to find out the envelope for only one period of Ts, because after that I know that I'll be able to repeat the same thing over and over again, right? So all the information at steady state I should be able to figure out, as long as I know what the envelope of V naught t will be during time 0 to Ts. Right? So that's the motivation of where we are going. So today's class is to figure out, with the process that we have so far cultivated in finding out the envelope of a LTV system, I'm going to use the same process to find out the envelope of LPTV system. But in case of an LTV system where there was no periodicity, what did you have to do? We had to evaluate the envelope at piecewise level, but for all t, right? T equal to minus infinity to plus infinity. But in this case, we don't have to evaluate it for all t. It's sufficient to evaluate it for one period. And conveniently, I can choose the period whichever suits me. I'm just choosing it from t equal to 0 to ts. I could have as well chosen from some 1.5t to 2.5t. No, I mean, it wouldn't have made any difference. Just that it is probably easier mathematically to evaluate something from t equal to 0 to ts. That's why I chose that that interval. Okay, fine. So that's having said that, in an LTV system, while figuring out this h of j omega naught t, we also did some piecewise analysis, right? What was that piecewise analysis for? Why was it necessary? It is time varying, and we wanted to see that if we have a section of time where I can evaluate things analytically, I would evaluate that only for that period of time. And then if there is another period where the system varies in a different way, I'll evaluate for that period of time and so on. So here clearly I see that there are two modes in which the system is switching between. Now this is particular to this setup, need not necessarily be true for all setups. But for this particular setup, it seems like there are two modes for which the system behaves like a piecewise LTI, right? When S of t is high, and another mode where S of t is low, right? So which means that I can then safely evaluate this into two, safely evaluate hj omega naught t into two regions. One region will be when S of t is high, and another region will be when S of t is low, right? Now, another important thing to understand is what is this t here? I mean, I have talked about it multiple times, but makes sense to talk about it again, just to refresh our memories. What does this t mean? Observation time, good, which essentially means that if I am evaluating h of j omega naught comma t, let's say mod of this t aligns with the t of S of t, right? So this is t. Right? So till now, see, I note that there is no tau in the picture, right? So what we are basically trying to figure out is, if I say t equal to 0, right? If I say I am evaluating h of j omega naught 0, which means I will get the value of the envelope at this point, right? Similarly, if I evaluate h of j omega naught t on, I will get the value of the envelope at this point. Correct? So similarly, if I have to do it numerically in a computer, all I have to do is to find out these values of these envelopes at different points from 0 to t on, and another set of points from t on to ts. And the computer is going to give me a set of data points, and that essentially is the envelope. And in order to find out the total output, I multiply that envelope with e power j omega naught t, and that becomes the total output. Right? Make sense so far? Okay. Yes.
And that can work at any time period, like first time period or second time period.
Right.
But there can also be some memory effect.
Yes, there will be. Not can be, there will be. It's a capacitor. There will be, exactly. But yeah, continue your question.
How are you saying that it is sufficient to work out everything for only one time period?
Yes, so the reason I'm saying that, okay, let me rephrase this question. He's asking is that there can be memory element, there can be memory effect. In fact, there will be memory effect because we have a capacitor, which means the response of the input at a previous cycle should affect my current cycle. Correct? So that is true for any LTI system also, right? Then how do we go about finding out a transfer function in an LTI system? We find out the impulse response. The impulse response contains the information of the memory, right? If there is no memory, the impulse response will also be only an impulse, a scaled impulse. Because you have memory, the impulse spreads, right? And that spread includes the memory information, right? And then we do a Fourier transform of that, and that becomes the transfer function. Exactly the same thing we are going to do here. We are going to find out the impulse response, and the impulse response itself will contain the information of the memory. And then we are going to prove a Fourier transform of that impulse response. Just that in case of an LTI system, that impulse response it doesn't matter where you are taking that impulse response from. It will always be the same. At whatever time t you take the impulse response, it will be the same. Because it's an LPTV system, it will not be the same. Right? The impulse response will be a function of t, and hence the envelope, the Fourier transform will also be a function of t. Correct? So that's the crux of.
Sir?
Yes.
So the impulse response won't be periodic.
What do you think? Good question. Will the impulse response be periodic?
Shouldn't be, because there's a capacitor towards the.
Okay, there is a capacitor which stores, but when you say impulse response, what do you, how do you evaluate an impulse response? Or rather, experimentally, how do you evaluate an impulse response? Right, but when you say impulse response, now you have to make the distinction between t and tau. In the sense that, let's say I am observing at certain point t, and I am trying to figure out the impulse response when I'm observing it at t. So then what are you, how are you going to think about it? You are going to say that I'm going to apply an impulse at tau before, incrementally before that observation time t, and increase that tau, right? From 0 to infinity. That is on the left-hand side, you are going to 0 to infinity, right? So at any point t, just say I choose a point t here. Let's say I choose to find out the impulse response at this point. That is, I'm observing at this point. Correct? So what will I do? I will say that the impulse has been applied at time tau before this point, and I am going to get a set of points, an array of points. So that is the impulse response at time t equal to 0. Correct? So now let's say I say that I do the same experiment sitting at this point, at the next stage. Can you comment on whether the array of points that I got with the previous experiment and the array of points that I'm going to get in this experiment will be same or different? Why?
There's different set of points.
No, think of it this way, right? So think of a lattice. The question is, okay, so maybe I repeat the question, then I'll answer. His question is the impulse response also periodic in an LPTV system? That's the question. Okay. So now my argument to you is, why do you think that so let me redraw. This is a very very important question. So I would like to spend a few minutes. So let me draw the S of t fully, or rather as much as I can draw. So let's say I am saying that I'm trying to find out h of t equal to 0, tau. Correct? So which means I am saying that this is my observation point. I have applied an impulse. I'm applying an impulse here and finding out. Or rather, let me say h of t equal to 0, I'm calling it 0, tau equal to 0. Will be the point that I'm going to get after I'm applying an impulse at that point and observing at that very instance, right? Similarly, I'm going to have another point h of 0, tau equal to, let's say, delta tau, which is slightly this side. And I'm going to keep on going h of 0, tau equal to infinity, right? So which means somewhere this side. I do the same experiment by now observing things here. That is h of Ts, that is t equal to Ts, tau equal to 0. So do you think this point that I'm going to get and this point that I got earlier will be same or different? Same, right? Similarly, what about this guy? Same, right? So if I go this way, I'm going to get the same set of points, right? So I can do this experiment for another set of points, saying that, let's say my initial observation, let's say t equal to some arbitrary t less than t on, let's say here. This is my observation point. Another observation point is this. I'm going to get two arrays of points. Will these arrays of points be identical or different? Same, right? But these 2 points, the arrays of points that I'm going to get from here and here can be different. Correct? So what does it mean? It essentially means that you are going to have a different set of points for the impulse responses that you are getting from each point from here to here. But that different set of points will repeat for every TS, right? So hence impulse response is periodic, right? Make sense?
Yes.
You had a question?
All this happening because for every shifting before same system undergoes same situation.
Correct.
That's why that all those
Correct.
changes will.
It's like an infinite lattice, right? It's like bulbulaya, right? So you go, you do not know where you are. Every room looks the same, right? So it's basically that. Right? Question?
T still have like number, like many number of tau lying between 0 to Ts, right?
I did not understand the question coming in.
Like when you're observing at T equal to Ts,
Hmm.
you'll still be having contribution of tau varying from 0 to Ts extra, right? Compared to the T equal to 0.
Why TS? Tau equal to 0 to infinity, I'm going to have effects of.
No, what I'm saying that the infinity at T equal to Ts is larger.
But is there a difference in the sense that, I mean, how many on cycles have you seen? Will you observe if you observe at T equal to 0 or T equal to Ts? It's the same thing, right? Infinity. It's like infinite ladder. I mean, that's how we do infinite series thing, right? We truncate the series, push it by 1, and then subtract, and all those things we do, isn't it? So now you are questioning the definition of infinity. That is a different old. I do not want to go there. How many types of infinities are there?
Array of point you meant the impulse responses, right?
Yeah. So if you do it in a computer, what are you going to do? You are going to apply an impulse. You're going to observe a value.
Vary tau.
Yeah. For each shift, you are going to get another point. That's an array.
Yeah, and maybe I'll do 100 observations.
Yeah. Right. So in next few minutes, we are going to find out that impulse response, exactly that impulse response. Okay. But the key thing to understand is that it is sufficient to find out the impulse response from T equal to 0 to Ts.
I think that's the green point that you drew after the pink one.
Mm-hmm.
After T equal to 0 only.
Mm.
It is supposed to be different what we observed at T equal to 0.
What do you think? Yes or no? Supposed to be different or not supposed to be different?
That's the same definition right there at T equal to Ts. Like
yeah, but the environment is not the same, right? Okay, you will understand. Let me do the derivation, then it will make sense. Okay. The derivation, when we do the derivation, it will make sense. Okay, so maybe we can proceed. Got stuck. So let me do the simple one first. So you will understand why I call this simple. It will not initially look to be simple, but it will eventually come out to be simple. Okay. So give me that latitude. So let's assume that I am trying to figure out what the impulse response will be if my observation time is at t on, right at this edge. Okay. So basically, I'm trying to figure out what is h of t equal to t on, comma tau. This is what we are after, right? Okay. So what are we going to do? We are going to apply an impulse. We're going to apply an impulse here and incrementally away from that edge of t on and find out what the voltage across the capacitor will be as I shift the impulse from t on to the left side, right? Make sense? Okay. So then tell me what this will be. So when tau is equal to 0, right, which means I've applied the impulse, and at that point of time, at that exact point of time, I'm trying to figure out what is the voltage across the capacitor. What will it be? Note that assume that I am just incrementally on the left-hand side of the falling edge, right? So it's just, yeah, it's just on, switch is just on. Then what will it be? 1 by RC, right? 1 by RC. Okay. So now I shift it slightly this side. Impulse, the applied impulse is tau away from t on, but tau is less than t on, let's say.
Like we are applying the impulse. We are observing from t is equal to t on to minus infinity.
Correct.
So impulse response will consider it from 0 to.
Yeah. So tau goes from here, right? So if you say tau equal to 0 is here, and incrementally I'm going to the left-hand side. So impulse is being applied incrementally at different points of time away from t on. So tau less than t on, what will be your impulse response? So this is t on. Yeah. So 1 over RC e power minus tau by RC, right? So, okay. So decay. So this decay will be of the form of 1 over RC e power minus tau by RC. And it will go and till t on, it is going to be like this, right? And this value will naturally be 1 over RC e to the minus t on over RC. Okay. So I am assuming, purposefully, I am assuming that the decay hasn't happened fully. If decay happens, there is no memory. Right. So I'm purposefully assuming that the decay hasn't happened. Right. The impulse response hasn't decayed off in 1 t on or 1 on time, right? The generic case, right? You can obviously make approximations based on requirement. So now let's say I have applied the impulse. What is h of t on comma tau where tau is greater than t on, just greater than t on? Tell me what will it be? No, look at it carefully. When I say h of t on comma tau greater than t on, when has the impulse been applied? What is the state of the circuit at the time? So the switch is open, right? So the impulse doesn't reach the capacitor, isn't it? So your capacitor voltage will be 0, right? Okay. So the impulse response will fall to 0. And then how long will it be 0 for? Which means Ts. Okay, very good. So till Ts. And then what's going to happen? So now, what is it? So imagine now, it's better to maybe I'll draw another cycle. So that will. So I'm still sitting here. Okay, hold on. So your tau is this side. Okay. So tau equal to Ts means this point, correct? isn't it? Okay. So now I'm saying that I'm applying an impulse at tau is equal to Ts plus delta tau, just above tau is Ts, right? So basically I'm applying the impulse here. The impulse here. And I'm trying to figure out what will this impulse response, what will be the value of this effect of this impulse, or the value the capacitor will retain after waiting for time tau, which is Ts at this point of time. What will be that value be? So when I applied that impulse, is the switch on? Switch is on, right? So when I applied the impulse, what is the value of the, at that point of time, what is the value of the voltage across the capacitor? Because the switch is on. 1 over RC, correct? Okay. So then immediately after application of the impulse, the switch turns off, right? So the capacitor holds on to that value of 1 over RC, correct? Then, which means the capacitor holds on to the value of 1 over RC till this entire period, correct? The class seems, is it confusing? Am I confusing you, or is it too simple? Okay, so think of it this way. So you applied an impulse, right? When you applied the impulse, the switch was closed. So it was a value of 1 over RC got stored. When 1 over RC got stored, the switch opened up. Correct? So, and this impulse is gone. Right? By the way, it was a voltage impulse, shouldn't have been current. But the switch is open. So now the capacitor holds on to the value of 1 over RC.
That impulse response, the impulse information after T on got lost, right?
Which case? That is a different case. This is a different case. So you are talking about here?
Yes.
Here it was not lost. That impulse never arrived on the capacitor because you are applying the impulse when the switch was off. Yeah. Okay. So in this case, the capacitor keeps on holding the value. But I am not interested on what the value of the capacitor at any point of time. I am interested on the value of the, I want to sample the value of the capacitor after waiting for time Ts, tau equal to Ts, right? So which means that till here, the capacitor is holding on to 1 over RC, but then the switch again turns on, correct? So the switch again turns on.
Second one is the what value, voltage value is the capacitor.
The entire thing is a voltage value of the capacitor. The capacitor will have a profile of voltage values. I am trying to find out the voltage value on that particular time on the capacitor that is of interest to me. It's T. The second one is T because I am trying to show you where incrementally where I am applying the impulse. Okay. Sometimes it becomes a bit confusing because it's not the traditional way of doing circuit analysis, right? We normally apply an impulse and then see with respect to time how it evolves. Here we are saying that my observation time is fixed and I'm applying the impulse before. It's like pushing the application instant on the left-hand side, right? So I'm reversing the way of thought process. So that's why it can take few minutes to get used to. But that's why I'm spending time on this also, right? So that things settle. So far, so good. Okay. So now, what I am still not where am I? I'm still not where that the point I'm after. I'm after this point. What will be the value at tau equal to Ts plus? Right? So means that I applied the impulse here. I have to find out what is the voltage value on the capacitor here. Right? So which means that because this entire thing is TS. Right? Okay. So what will be the voltage value? This value will be 1 over RC to the power minus T on over RC. Correct? Because here it had 1 over RC. It will decay. And I will get this value of 1 over RC to the power minus T on over RC. Okay? So this is exactly the same as this value. Correct? Okay. And then I incrementally apply, move this application instant to the left further. What am I going to see? What will the h of t on comma tau look like? So what I mean is this impulse is now moving to the left, right? I applied the impulse here. So what will it look like? What is the value of voltage that I am going to sample on the capacitor at time t equal to t on? It will drop by the same profile, right? E power minus t over RC, right? So it is going to drop again, right? So it is going to drop again. And again, it is going to go again to 0 after this time t on. And this is going to repeat, right? So this is going to be like this. Does that make sense? So interestingly, if you think about it, if I join all these seemingly staircase things, it kind of becomes an LDI network, right? It will become 1 over t, e to the minus t over RC. Just that it looks like I am breaking that discharge of the capacitor, almost like that. I'm breaking the discharge of the capacitor after applying an impulse. It's similar to that. And that should make sense because the switch is turning on and off. So whenever the switch is off, the capacitor is not discharging and so on. It looks like that, similar to that. Questions so far? Okay. If there are no questions, then the next order, yes, questions.
What are the considerations you take under the test?
Okay, you mean how did I come up with this?
For that case, the whole case,
Okay, can you
what are the things that we consider at the deriving that case, above case?
okay, so why don't you tell me what did you take away from it? Then I can interject.
Because I unable to means compare above case with below case. I did not map that.
Okay, you mean that these two,
Hmm.
this and this.
The conclusion I get from case one,
Huh.
what are the conclusions I get from case two? I do not.
You're not able to match.
uh,
Okay,
map.
okay. So can you okay, so where did I lose you? Can you help me understand? Then probably I should be able to interject. So where do you was this fine? Or this was also not fine? This part.
Similar things are in that thing, in that axis there is tau and below axis is t.
Correct.
But where we apply the impulse at an above case.
Okay. So here in this case, we are not, this is basically the voltage that I am observing on the capacitor as the impulse has been applied at different points of time, and that this is tau. And what does tau mean? What is the definition of tau? Tau.
From observing time to where.
Yes. So basically, if you can assume this tau implies impulse has been applied at, is applied at t on minus tau. Correct? At t is equal to t on minus tau. Impulse has been applied at t equal to t on minus tau. Now, can you relate these two graphs? Or maybe I can also spend some more time on this. So let's say when tau equal to 0, which means impulse has been applied at
Same.
T equal to T on, right? So hence you are getting 1 over RC, right? So if tau equal to non-zero but less than T on, you are getting this decay. Now the fun starts when tau is just above, tau is just above T on, that negative T, right? In the way I have drawn it, it's negative T.
The point moves that side of the origin.
Correct. So the application instant now is on slightly negative value of T, but at negative value of T, the way the switches are functioning, S of T is off, right? So the no response of the impulse proceeds on the capacitor, correct? Which means the value sampled on the capacitor will be 0. So hence you see that this goes to 0.
Means we are moving that in this way.
Correct. We are moving the application instant to the left-hand side.
Finding what is happening at T on.
Yeah. What is the voltage on the capacitor at T on?
That's why if you move tau greater means that that side of the negative axis of the origin, that there is no voltage, means there is no switch on. That's why in the
Correct.
observation point it goes below.
Correct, but not till infinity. It is till the time when switch is off. But if you go beyond TS, the switch turns on again. Right? So hence I get this. So this one is because the switch turned on again. Right? Now note that the important thing, the mental model that you need to understand is, this is not the value on the capacitor when the switch had just turned on. Right? Because I am not looking at tau equal to 0. Now I'm looking at tau equal to TS. Right? So which means that even though the capacitor voltage is 1 over RC, I still have to wait till TS to see what the capacitor voltage comes to and then pick that value. Right? So I'm waiting till TS. So in that process of waiting, so imagine this is where I had imagine this is T on, right? So which means I had applied the impulse here and I have to wait till here. So the capacitor was holding a value of 1 over RC here, and then it discharges and comes here. This value will be this value, and incidentally this value is the same as this value, because applying a impulse here and waiting is no different from applying an impulse here and waiting, because nothing happens in the off period. Right? Hence we have this continuity of voltages. Right? That's why I made that comment that it seems like if you take away these off periods and just collate all these bumps together, it would look like e power minus tau over RC. Right? Okay. So note that this is an exercise for h of t on comma h of t comma tau for t equal to t on. The same exercise we have to do for all values of t between t equal to 0 to ts. Right? Make sense? In an LTI system, 1 is enough, because there is no difference doing the exercise for t equal to t on or t on plus delta t or whatever. In an LPTV system, you have to do it for all points in the cycle. Okay. Now, the next thing to appreciate is the fact that why are we doing this impulse response? Because I want to find out the response to e power j omega naught t. Right? So how do I go from impulse response to a response to e power j omega naught t? I do a Fourier transform. Yeah, and multiply the effect of the Fourier transform with e power j omega naught t. That will be the final output. But the envelope is basically the Fourier transform of this waveform. Right? So if I do a Fourier transform, I'm going to get something, right? Some value I'm going to get. But what would that value signify? What would I get from that value? What would it mean? By the way, I'm going to get, if I do this exercise, I'm going to get these different kinds of sequence for each point from 0 to t equal to 0 to ts. We agree? And I do a Fourier transform for each of those sequences. So I'm going to get different values of those Fourier transforms from t equal to 0 to ts. So what would those different values mean? What does the value of a Fourier transform mean? From the perspective of application of a complex exponential, can you relate? Let's say forget about LPTV. In general, what is a
Strength of the signal that you combine.
basically the strength of the envelope of e power j omega naught t is basically the Fourier transform, right? In an LTI system, it is sufficient to find out the strength at any point of time because the strength of that envelope does not change. Right? For t equal to 0, infinity does not change. The strength of the envelope remains constant. It's a function of omega, but with respect to t, it does not change. It's an LPTV system, which means that the strength of the envelope will also change. That's why we need to do Fourier transform for each of these sequences that I'm going to get from here to here. Does that make sense? Which means that after I do this Fourier transform, I'll do the Fourier transform, but it's better to understand why we are doing these things before going and do the maths. So with respect to t, if I do a Fourier transform, I was doing till t on, right? The entire thing h of t on comma tau we did. So let's say I do a Fourier transform of h of t on comma tau. I get this sum h of j omega comma t on. In plain English, what does this mean? It means that the strength of the envelope at time t equal to t on, right? And because it's an LPTV, by continuance, it means that it's the strength of the envelope at t on plus ts is the same as the strength of the envelope as t on plus 2 ts and so on. Okay? So which means that I'm going to get a value of h j omega t on, and that value will be this. So if I say the mod of h of j omega t, so this value that I'm going to get will be mod of h of j omega comma t on. Right? And if I do the same thing at t on plus ts, I don't have to redo it again because it's an LPTV system, I know that this value will be same here and everywhere else. But there is no guarantee that this value will be the same for any other t. If I do this here, let's say, I'm going to get a different value, probably this one. But this value will be the same as this value here and this value here and so on. Correct? This will be a Fourier transform of mod of h of j omega comma some t on minus delta t, let's say. Correct? Similarly, I'm going to do another one maybe here. So I'm going to get something same here, same here. And I'll get the set of Fourier transforms. Right? So if I take sufficiently close number of points from t equal to 0 to ts, and I get a set of Fourier transform, which means that I get the strength of the envelopes. All I have to do is multiply that with e power j omega naught t, and I get the envelope of I get the final waveform v naught t without any approximation. Okay.
So by envelope, you mean that
by envelope, I mean this. Yes, it's basic, but strictly speaking, if you have an LPTV system, or rather LTV system, if you apply e power j omega naught t, your output will be something times e power j omega naught t. This something is also a function of t because it's an LPTV system, and this is the envelope. Right? This is the envelope. In principle, you can say envelope is equal to output when input e power j omega naught t is applied divided by e power j omega naught t. Okay. Right? So the sequence of thought is clear, right? Because that is the most important thing. If you know what to do, doing is not a problem. Okay, fine. So let's do the Fourier transform of h of t on comma tau. So this is pure, I mean, there is no intuition. This is simple brute force. Okay. So anybody knows how to do a Fourier transform of this? In your maths classes, was anything covered? It's okay if it's not, then I'll just. So this is firstly, this is looks like an infinite series, or rather, it's a. So these blocks repeat infinitely, but in a scaled format, right? Each time it is scaled and repeated. So can you guess what will be the way of doing the Fourier transform? And then no, it's not a repetition. It's not an exact, it cannot be Fourier series. In general, when you treat with infinite series, you can to some extent, but again, that will again be, the scaling factor has to be taken into account.
Yeah.
Right? So think of your class 12 maths when you used to do this infinite series, right? You had to scale, you broke them into kind of, right? No, forget about rectangle. I'm not talking about calculus here. So when you do, let's say you have one series which is 1 plus 2 plus 3 plus 1 by 1 square plus 1 by 2 square plus 1 by 3 square and on. Yeah, right? And then you shift and you subtract, then you get one piece and then do this side and that you get, right? Exactly, that's what you're going to do here. Yeah, kind of similar, right? So I can say that I'll drop this t on now. I'll just say that h of tau. So in this case, I can simply say that this h of tau. So let's say I shift this entire thing to the right by 1 ts. If I shift this entire thing to the right by 1 ts, I'm going to get this. But this guy will be 1 over RC. But here we had 1 over RC e power minus t on by RC. Correct? So I can say that h of tau is equal to, now is equal to, so by the way, this is what? This is h of tau minus ts. No, I'm dropping the t on. Let's see, because this is at t on. So this is a shifted version of h of tau by ts, right? I simply shifted it by ts to the right. Now, what is the relationship between the top and the bottom guy? I can simply say this is equal to this shifted version scaled by e power minus t on over RC. So what I'm saying is h of tau so h of tau, that is the top one, is I can say is a scaled version of h of tau minus ts times e power minus t on over RC. But if I simply do that, I am losing out on this part, this guy. I'll say this is plus some p of tau, where I define this to be as p of tau. Make sense? So p of tau, by the way, is only, p of tau is only this much. Right? We're okay with this expression? Okay. So now things are simple because now I can simply do Fourier transform of both sides. So I get h of j omega, comma, I will just write t on because it is happening at t on, just to remind ourselves it is at t on, which is equal to h of j omega, it is power minus j omega ts times e to the power t on over RC plus some Fourier transform of P of t. Correct? So h of j omega comma t on becomes P of j omega by 1 minus j omega ts times e power minus t on over RC. Okay, so now you see we are in a fairly simple territory. All we have to find out is the Fourier transform of P of t, which should not be very difficult because P of t I can express as, or P of tau, I can express as e power minus tau 1 over RC times e to the power minus tau over RC times u of tau minus u of tau minus t on. Right, where u of tau is the unit step function. Okay, so again I can break this up into 1 over RC e power minus tau over RC u of tau minus so I'll just have it as tau minus t on here so that I can do easily the Fourier transform. So your P of j omega thus becomes, the first one is simple. It is 1 plus 1 by j omega RC. And the second one is the shifted version Fourier transform, which means I'll multiply by e to the power minus the shift, which is power minus j omega t on e to the power minus t on over RC. Okay, so the total h of j omega t on becomes P of j omega times this guy. Correct? So I'll simply write it as okay. So this is your strength of the envelope at time equal to t on, time t equal to t on plus ts, and so on. Okay. Any questions so far? All good? Okay. So similarly, we have to do it for all other t. We'll do it for another case, all other t, but it is instructive to stare at this expression. It might look a bit complicated, but it is, we can break it down into smaller pieces for different points of different situations of RNC, right? So that's what we are going to do next, right? And then after we are comfortable staring at this expression and we understand how this expression behaves intuitively, then we'll go into generalized T. Okay, so let's stare at this expression for the time being. Now I'll tie it up with the situation where which we talked about in the previous class, that is RC to be much greater than the on time, right? So we'll make that approximation. So the case is RC to be much greater than DS. Okay. Okay. So now let's see what is happening at various values of omega. At omega equal to 0, that is at DC. Okay. At DC, what is this value? H of 0 t on. It's clearly 1, right? Because all the e power j omega t on goes to hold on, something's wrong. Yeah, right. So at omega, rather at omega tends to 0, you are going to get this to be approximately equal to 1, because if you put the limit, it will be like 0 by 0 format. If you put the limit, it will go to close to 1. Okay, so that's not too much of fun, because we understand that, right? At DC means you have a constant input, right? And the voltage across the capacitor will be that input. So that's fine. That's fine. Now, what we are interested in is to find out what is happening beyond DC, right? Let's say assume omega equal to delta omega, where delta omega is less than is tends to 0, right? So let's say I say h of j delta omega. So what do we see? So here in the denominator, I see h1 plus j delta omega RC. In the numerator, I see 1 minus so I will expand the numerator and the denominator in the Fourier, in the Taylor series format. So in the numerator, I get 1 minus, this is 1 plus, or rather. Okay. So
Just also assume that T1 is also much less than RC.
that's implied, right? T1 is less than TS. So that question? You had a question? Okay. Okay. So in the numerator, I get okay. So I multiply with what should I multiply with? Let's multiply with RC by T on both the numerator and the denominator. So we get 1 plus j delta omega RC. Okay. And if I say that, if I apply this condition, that not the condition, let's say TS by T on is essentially the duty cycle, right? So I'll for this time being, I'll call this N. You'll understand why we'll call it N later. So this is the duty cycle.
It's 1 over 2.
It's 1 over duty cycle, correct. So it is 1 plus j delta C. So this guy cancels out, right? Kind of. So this cancels out. So you get 1 by 1 plus j delta omega in RC. Okay. So what does this remind you of? It's a low pass filter with a time constant of NRC, right? So firstly, take away at just above DC, right? It behaves like a low pass filter. But the key thing to note is that it's not a low pass filter with RC, not a low pass filter with 3 dB frequency of 1 over RC. It's a low pass filter with 3 dB frequency of 1 by NRC. Right? So that is one key takeaway, right? So LPF with omega 3 dB equal to 1 by nRC. This n is important. Okay, so which means you can arbitrarily make it narrower and narrower by increasing n. Basically, you make the T-on to be smaller and smaller with respect to Ts. You can get sharper and sharper, or rather, I should not say sharper at this point. You will get smaller and smaller bandwidth of the low-pass filter, right? It is equivalent to saying that almost like you have increased the value of R the n times, because on an average, the R is on 1 over nth the time of the cycle, right? So if R is on for the entire cycle, it's R. Imagine you are drawing charge from the source, right? So if the R is on, basically the switch is on for the entire cycle, the amount of charge that you are going to draw will be n times higher than the case when the switch is off, which is modulating per cycle. So it is equivalent to say that intuitively that I've increased the value of R by n times, because I'm drawing n times lesser charges, right? That's a very crude way of thinking about it, but that's one way to understand why your 3 dB frequency, why your effective R has increased by n times. Okay. Okay. So now this is also not, this is interesting, but still fine. We understand that. But in a low pass filter, right, if your 3 dB frequency is 1 over nRC, if you are applying an input at much higher frequency than 1 by nRC, what do you expect to happen? It should get attenuated, right? But let's see what happens in our case, right? Something very interesting happens. I'll make the approximation that I'm talking about the case of h of j omega equal to omega s. Let's say I'm finding omega s t on, where omega s is 2 pi by ts. Okay, I just arbitrarily chose one because everything is repeating at omega s. So instead you have to understand what is happening at omega s. Okay, so let's do the math. So this is 1 by j omega s RC. Then I had two expressions. In the numerator, I had 1 minus minus t on over RC times e to the power minus j omega s t on, right? Right, yeah, omega s t on. And in the denominator, I had this term remains the same. And this becomes e to the power minus j omega s ts. Right? Okay. So now, can you comment on this term with respect to 1, omega s RC? Is it comparable to 1, much lesser than 1, much greater than 1? It will be much greater than 1, right? Okay, good. So I can drop that 1 plus. So I can basically say this is 1 by j omega s RC. So can you comment on this? Yeah, omega s ts is 2 pi. So this is 1. So I don't have to bother. So this is 1 minus e to the power minus t on over RC times e to the power minus j. T on with respect to ts is what? So we basically said ts by t on is equal to n. No, we don't know n, right? So this is 1 minus j omega is
You're calling n duty cycle, right? So
yeah.
it will be 1 over.
No, 1 over n is the duty cycle. I mean, n is more than 1, right? So right. So this is omega s times ts by n, right? So basically 2 pi by n. It's 2. Correct? Okay. So now I need a value for n to appreciate what's happening. A very common value that people use in literature is 4. We'll get to why 4 later on, but let's use 4 for the time being. So let n is equal to 4. So then much time? 1 by j omega sRC times 1 minus e to the power minus t on over RC. Now, what is this? E power minus j pi by 4, which is basically j minus j. Correct? So this j. Okay. Next step is basically to break it up. The denominator becomes effectively 1 minus t on over RC, which is t on over RC, the approximate. And the numerator is approximately 1 plus j. Correct? Okay. So this goes. So you get 1 plus j by j times 1 by omega st on, which is omega s times ts by n, which is 4. So this is 2 pi. So you get 1 plus j by j into 2 by pi. Correct? Okay? Huh?
Minus t on RC.
No, okay. A good question. So, yeah, so this is probably I need to spend a minute. So here I consider this to be e power minus t on over RC to be 1 minus t on over RC. Right? But here I consider this to be approximately 1. Why? Huh? No, there is a reason to it. What are you, when you approximate, you are always neglecting something. What are you neglecting with? If I consider here e to the power minus t on over RC to be 1, I am neglecting something with respect to 0. No, that is true. But I mean, the question becomes that when can I approximate e to the power minus t on over RC as 1 or 1 minus t on over RC? Obviously, the second one is a better approximation than the first one. Right? But I mean, I purposefully chose to ignore this better one in the top case. The question is, what impact does it have, right? So if I do that, let's say I do not ignore. So in the numerator, I say it is still 1 plus j, 1 minus t on over RC. Correct? So what do I get? I get 1 plus j. So 1 minus t on over RC plus j. Now can I ignore t on over RC with respect to j? I can. Okay, sorry. Yeah. Okay, so in this case, can I ignore t on over RC with respect to 1? I can, right? So this becomes 1 plus j. So now, but in the bottom case, right? No, why? Oh, fine. Understood. Even if you ignore, in the bottom case, what is happening? 1 minus e to the power minus t on over RC. If I assume t on over RC to be 1, then this becomes 0. Right? Your error is infinite then. Right? So it is equivalent to saying, I'm giving an analogy, not particularly true in this particular case. Let's say you have a number, theta, or let's say you have, just take a number, let's say 1. You are adding 1 to a million, and you are doing 1 minus 1. Right? So in which case can you neglect 1? Right? So the same thing here, right? So what is the impact of that neglect of that approximation? So the impact of that approximation is huge if I do not do that 1 minus this one in the denominator. But in the numerator, that impact is negligible. Hence, I am making that approximation, right? Okay. So now the key thing to note here is that we had just in time to get to the most important part of this, times 2 by pi, which means the mod of this h is this is root 2, so 2 root 2 by pi. right? So this is approximately 1. I mean, slightly less than 1, but approximately 1. Now, what is this telling us? The switched RC network, whose 3 dB frequency was supposed to be 1 by NRC, right? But now I applied an input at omega s, much, much higher than 1 by NRC. Your output is not dropping. Your output is significantly, it's almost close to whatever your output you are getting at DC. And I can do the same analysis for omega equal to 2s, 2 omega s, omega equal to 3 omega s, omega equal to 4 omega s. I'm going to get that. Right? So this type of behavior you are not going to get in an LTI system. Okay. So the reason we do not have time in this class to give you the intuition, but intuition to some extent should be evident from the previous lecture that we had where I talked about the architectures. You can think of it as the trick that we played here was input was at the same frequency as a switch, right? In this case, your input is at the same frequency as the switching frequency, which means, again, if you recall the previous lecture where I talked about this N-path architectures, I can assume that, yeah, right, it is seeing the same section of the input. It's not drawn properly, but yeah. So kind of you are seeing the same section of the input, hence it is averaging for omega equal to omega s. So it is almost like it's seeing a DC for those small periods of time, right? But if you go away from omega s, it is going to average it out. So we'll do it next class. If you can do it yourself, instead of putting omega equal to omega s, put omega equal to omega s plus delta omega and see how that expression evolves. You're going to see the expression evolves almost similar to the previous case where we had the 3 dB frequency and all. So what you are going to see is at omega equal to omega s, if I plot with respect to omega, this omega is the input, you are going to see a high value here at 0 at DC. Then omega s also you're going to see a decent value, 2s also is a decent value. But in between these, you are going to see this drops. You're going to see this comb-like structure, right? So we saw this kind of behavior intuitively in the previous lecture, if you recall this multiplication with respect to switches and capacitor impedance getting moved, shifted and all. So this is essentially a more rigorous mathematical way of coming at it. Yes, yeah. And it's basically we have this comb-like structure which keeps on repeating at every omega s. Okay. Okay, fine. We'll stop here.